So what have we invented as a new cycle? This is the turbojet with afterburning. And what are the results? So we are increasing VA, F divided by Vjet, F divided by m dot, and F, we are increasing all this by 1.5. This is, so Vjet A, Fa divided by m dot, that is not changed, and Fa. But at the same moment, the TSFC has been increased by a factor 2. This is the TSFC A. Because m dot F is changed to m dot plus m dot Fa, that is approximately equal to 3 times m dot F. So this is the result we have. Something that is also sometimes said is that we are playing with the thrust to mass ratio of the engine. So that after burning or post-combustion is impacting largely the mass, the thrust to mass ratio. Because we are increasing the thrust, and we say sometimes that the mass of the engine is the same. Why do we say that? This is because m dot is the same in both in both engines, on both sides. But this is in fact not true. We could have the impression that the mass of the engine is the same because we have the same mass flow rate. But in fact, the mass is increasing compared to what we had here before. And we increase the thrust by a factor 1.5, but here we are increasing the mass because we are adding a fuel pump, we are adding an igniter with all the electronics needed, we are adding flame holders, we are adding some injectors, we are all adding also a second skin to the exhaust nozzle, and certainly you will increase the mass here by 10, 15, maybe 20%. Especially that there is still another element that we need to add to the mass that I will discuss in a minute. And so the let's say, affirmation that is sometimes coming that we have increased the thrust to mass ratio of the engine is not really so true, because we are rather much increasing the mass of the engine by all what we put in the exhaust section. A second discussion we can have, this is related with when will we use this? Because maybe we are increasing the thrust by 50%, but we are increasing the fuel flow by a factor 3. That means that we are reducing the length of the mission by 66%. We are reducing the length of the mission by a factor 3. So the mission that was 3 hours, now it's only 1 hour if you are using continuously the afterburning. So something you can say is that due to this number here, you will use the afterburning during very short periods. You will use it just when it's absolutely needed. During a few seconds, a few tenths of seconds, maybe 1 or 2 minutes, but not more in a row. Short periods of time. And you will do that when it's only absolutely necessary. So when you need to have this increase of the thrust by 50%, 1.5 higher. When are you using that? When is it necessary? When do you need F multiplied by 1.5? When do you need 50% more thrust? A general way to express that can be to say when you are doing difficult maneuvers. So when you are doing difficult maneuvers, you will need an extra thrust in order to be able to perform this maneuver. The first one, this is takeoff. When you are taking off with a very heavy aircraft or from a very short runway or a heavy aircraft on a short runway, you will need to decrease the takeoff distance because you are too heavy or because the runway is very short. And the only solution is to use the afterburning. The afterburning will decrease the thrust by a factor 1.5, so it will have a direct proportional impact at the level of the acceleration and at the level of the distance needed to take off. Also, for some maneuvers in flight, you need to remember that we are always considering F minus drag multiplied by the flight speed divided by the gross weight. This is expressing what we called the specific power, or what is also noted SEP, the specific excess power. And this is in order to accelerate. You have a thrust minus drag, so if you have a thrust larger than the drag, you are able to accelerate or to perform some maneuvers. And of course, if you put here FA minus drag, then you are increasing at a sudden the excess of power you need to do some maneuvers, like climbing, like taking a turn, like accelerating in a turn. I don't know what you want to do in a combat evolution, for example. It is also typically the example when you need to take off from an aircraft carrier, where you have a very short runway. If you are a load, of course, to use the afterburning, because it's not always a load, because you will maybe degrade the runway at the deck of the aircraft carrier by using the afterburning. But it's also a way to take off from an aircraft carrier. The second case, this is to go to through the transonic. In the transonic region, from let's say 0.9 up to 1.2, 1.25, you have a huge increase of the drag. In order to be able to fly through this zone of the Mach domain where you have a higher drag and not spend too much time to go through the transonic domain, the only solution in a lot of cases, the almost only solution, this is to select the afterburning. So you will go to Mach 0.85, 0.9, you will select the afterburning, you have an increase in thrust, you go through the transonic, and when the drag is starting to decrease again from Mach 1.2, 1.25, 1.3 maybe, you will deselect the afterburning and you will continue your flight at supersonic speed. So through the transonic, it's absolutely necessary to go in afterburning. And then the third case, it is the supersonic flight. In a lot of applications, in a lot of aircraft, you need to stay in afterburning in supersonic flight. To accelerate, certainly in supersonic flight, but even to cruise in supersonic flight, you need to have the afterburning selected. If you do not need in cruise the afterburning selected, you are flying in what is called the supercruise capability, or you have the supercruise capability. That means that you are flying cruise supersonic, Mach larger than 1, without the afterburning. But very often, this domain in which you are able to supercruise is a very limited one. For very often in the region maybe of 1.4, maybe 1.6. So because the transonic, this is the drag in function of the Mach domain, this is something that is like this. Like this. And so when you are here maybe at 1.2, and sometimes it can increase like this, you can go maybe up to 1.5 or 1.6, and it's already increasing here from there 1.4. So here in this zone maybe you are not forced to have the supersonic afterburning, but at a certain moment, because you will be in this zone, the same as where you had to use the afterburning during the transonic, you will need again to use the afterburning above a certain Mach number. And most of the aircraft that are able to fly at supercruise, so in cruise at supersonic speed without the afterburning, it will be limited to a range like this one, around 1.4, 1.5, 1.6. Of course, it depends how the drag is increasing in function of Mach number. If you have a drag that is increasing like this, maybe you will be able to go and fly at Mach 2, Mach equal 2.0, without afterburning, if you have a drag that is not increasing too much. This is, for example, the case of the Concorde. The Concorde was a very thin aircraft with a length over diameter ratio that was optimized for supersonic flights without a too large increase of the drag. And at Mach 2.0 in cruise, the drag was not so high, and it was possible to supercruise, to have not the afterburning selected, enough thrust coming from, let's say, the normal operating turbojet. It was a turbojet, is what we have discussed here, without the afterburning. But it's very rare that you have such an opportunity, and if you are able to do something like this, it will be at a very precise Mach number. So not at another one. Because don't forget that the thrust is equal to m dot v jet minus VA. And so when you increase the Mach number, this is increasing a lot, and so it is negatively impacting the evolution of the thrust. But I will show you in a slide the evolution of the thrust with afterburning in function of VA. And we will see that the evolution of the thrust with VA, when you are above Mach 1, this is a curve that is like this, in fact. The curve is increasing because you have an effect of this. And